We often think of earthquakes purely as disasters, but scientifically, seismic activity is actually one of the most important sources of information we have about the interior of the Earth. It acts almost like an X-ray, allowing us to see what lies beneath our feet. So, what exactly is an earthquake? In its simplest terms, it is the shaking of the Earth caused by a sudden release of energy. This release generates waves that travel in all directions, much like ripples in a pond. But to really understand why the Earth shakes, we have to look at the mechanics of the crust. I want you to imagine a specific geological feature known as a fault. A fault is a sharp break in the crustal rocks of the Earth. In this scenario, you have rocks near this fault line that tend to move in opposite directions. However, they don't just slide smoothly. Friction holds them together. Think of it like two rough pieces of sandpaper pressed against each other. They are stuck. But, at some point, the force of their movement overcomes that friction. When this happens, the rocks slide past one another violently. This sudden slip is what causes that massive release of energy. We need to define two critical terms here regarding location. First, the point where this energy is actually released, deep underground, is called the focus of the earthquake. You may also hear scientists refer to this as the hypocenter. Second, the point on the surface that is directly nearest to the focus is called the epicenter. Because it is closest to the release of energy, the epicenter is the first place on the surface to experience the waves. Before we identify the specific waves, we need to understand the physics of how they travel. Earthquake waves are fundamentally divided into two categories: body waves and surface waves. Body waves are generated at the focus, the epicenter's origin point, and move in all directions, traveling internally through the body of the Earth. This is why they are called body waves. They move through the Earth's interior. As these waves travel, their behavior changes based on the material they pass through. We know that denser materials are generally found deeper downwards in the Earth. The rule of thumb here is, the denser the material, the higher the velocity of the wave. Furthermore, as these waves encounter materials with different densities, they reflect or refract, which changes their direction. Interestingly, when seismic waves finally reach the surface, the materials there have a lower density compared to the deep interior. This change in density actually slows down the intensity of the waves. Let's look closer at those body waves. They are split into two specific types, which we call P waves and S waves. P waves, the P stands for primary waves. These are the first ones to get recorded on a seismograph. You can also think of them as pressure waves. They travel quickly. Unique capability, they can travel through both solid materials and liquids. Motion, they force the ground to move backward and forward, compressing and expanding the material. S waves, the S stands for secondary waves. These come after the primary waves. You can also refer to them as shear waves. They travel more slowly than P waves. Motion, they create a swaying, rolling motion. Crucially, they shake the ground back and forth perpendicular to the direction the wave is moving. Finally, we have the third section of the seismograph reading. When body waves move toward the surface and interact with surface rocks, they generate a new set of waves called surface waves. These are the last to report on the seismograph. While they arrive last, do not underestimate them. Surface waves are the most destructive and damaging of all seismic waves. They spread across the surface of the Earth and cause the physical displacement of rocks. This displacement is what leads to the collapse of structures, which is the primary cause of danger during an earthquake. While the initial tremor lasts seconds, the damage can persist for generations. First, direct structural damage, collapsing buildings, bridges failing, roads buckling. This is what immediately traps people and claims lives. Next, infrastructure breakdown, severed gas lines spark fires, broken water mains hinder firefighting, and downed power lines create blackouts that paralyze communities. Then come the cascading disasters, landslides burying entire neighborhoods, soil liquefaction where solid ground turns to liquid, and tsunamis that can wipe out coastal communities minutes after the shaking stops. We saw this in Japan 2011 when the tsunami multiplied the earthquake's devastation exponentially. Ultimately, earthquakes don't just damage buildings, they rupture communities, economies, and and sense of security for years. Understanding these interconnected damages helps us build smarter, prepare better, and create more resilient communities. Thank you.